This is the fifth review video on ecology, and we're starting in population ecology here. First thing we talked about was density and dispersion. Density, excuse me, is the number of organisms in a given area, and you just take the value of your organisms, divide it by the area to get organisms per whatever your unit is. Dispersion, we looked at three different examples. We looked at clumped, we looked at uniform, and we looked at random. Clumped is when there are locations that are more favorable. So, for example, if you have a forest floor, the mushrooms are going to grow maybe on a log. Starfish are going to be found in tidal pools, cracks in a sidewalk where plants can grow. Uniform, this is often the result of territoriality or a defense mechanism where one organism will keep the other organisms at bay. And one example would be a squirrel fish, the bottom of the ocean in their nook, and they keep other squirrel fish out of their area, or a lot of organisms or a lot of species are territorial. Random, this depends on abiotic factors like wind blowing seeds or water washing things up, bird droppings. So you could see any of these three. Then we talked about how can you measure a population? So you can do a direct count, like if you had trees in a given area, you could just count the trees. But if you have a population that fluctuates, you'd probably want to use the mark recapture method. So you have this formula where N is the population. And we have S and X. You should know about the types of ways to do population sampling, but you aren't going to have to do any calculations. But to review, S is the first capture, and the order is you would want to capture, and the amount that you capture the first time is S. Then you would release them. The second capture, the total is N. And then the second capture, the ones that are marked are X. So you take the amount you captured the first sampling times the amount you captured the second sampling and divide that by the amount that were marked. And that gives you an estimation of what the population size would be. After mark recapture, we looked at life tables, and it gives you information on population growth and the average number of offspring born to an individual. Here's fecundity. And this is females only. We spent quite a bit of time on survivorship curves. So we have the first example here. And we said these are case strategists. These guys have very few offspring. They have a low death rate early, but it becomes high later. And they don't have very many offspring. These are R strategists. Where they have a lot of offspring. So we looked at oysters and we looked at seedlings. And they have a very high death rate early on, and then it slows down. And we'll look at R strategists and case strategists on a slide coming up here. The other thing is case strategists are type 1. R strategists are type 3. Type 2 means you have a constant death rate over the course of the species' lives. So they gave an example of a bird here, or over here, a squirrel. We talked about growth. So we had exponential growth, right? And this is a J curve, or, exponential curve. And what happens here is when we have population growth and there's no limitations. So bacteria in an area where there's unlimited room to spread out and unlimited food. We have equations for each of these. So our first equation for exponential growth was N final, number 1 plus R to the T power times the NO, where R is the rate of change. Births per 1,000. rate of change. N sub O is the starting population. T is the time of the cycle. And NF is the final population. But this rate of change, we can say that this one you will see on the final. This is deaths minus births divided by N sub O. So the rate of change is the amount of organisms that we have that are being born versus the ones that are dying. And what we want to know here is, what do these pieces mean and what does it mean to have a rate of change? So the questions on logistic growth versus exponential growth are going to be more conceptual than they are going to be calculations, as opposed to the test that we took over this chapter where we had quite a few calculations. But I'd like you to understand that the conditions under which you're going to get exponential growth and what the how this equation differs from the logistics growth equation, which we're going to see on the next slide. So logistic growth takes into account carrying capacity, which is the amount of individuals in a population that the environment can support. Our equation for logistic growth is NF equals R NO K minus NO over K. So again, R is going to be our rate of change. NO is our starting population. But here we have K, which is carrying capacity. So when we look at this, as we initially start off with that exponential growth, but as our resources are limited, or we have a factor that affects the ability of these organisms to reproduce, we begin to level off, and we get this shape of a curve. If we have, so it's not affected by lifespan. Lifespan affects growth, but not the resources. But what this tells us is that if we go back to the equation, if K is greater than N, we get fast growth. And if you look at these values, so you're multiplying here, if K is less than N, you have little to no growth. And this just makes sense. If your carrying capacity is a lot higher than your population, you have room to spread out. But if you're getting close to your carrying capacity, you're running out of resources, you're running out of space, you've got a buildup of waste, there's something going on. So again, for final, no calculations, but make sure you understand rate of change. Make sure you understand that this equation takes into account, you don't have to memorize the equation, but make sure you understand how carrying capacity in the equation or in the graph are different from your exponential growth. Here we have R strategists versus K strategists again. So again, we said R strategists or type 1 have many offspring. They don't live long. Their organisms are usually small. When we look at the organisms that are larger, like elephants or whales, those are going to be K strategists. And they don't have to invest a lot of their energy to create their offspring. It's a relatively given short period of time. And as opposed to that, K strategists, we get very few. So think about elephants or whales. They have one calf or one offspring or one child, or I don't know what you call a baby elephant. They live a long time. And think about how much time it takes to raise a child, even for people. They say it takes $1 million to per child to raise a child in Western society. And again, our larger organisms we see, elephants, whales, are K strategists. We had density dependent and density independent factors. If we look at this, the density independent death rate does not change. And here a density dependent birth rate would be affected. So as your population density goes up, your density dependent factors are going to drop down because there's more competition for resources. So here we go. Density dependent limiting factors operate strongly when population density reaches a certain level. These would be density independent because a natural disaster, if it takes out 30% of your population, it doesn't matter if it's 100 organisms or 1,000 organisms, it's still going to be 30%. Same thing with unusual weather. But competition, predation, parasitism and disease, and we said here, this is sometimes caused by waste buildup. So this is affected by population size. Competition, here we'd be talking about territoriality. Predation, and so forth. So these are examples of things that would be density dependent factors, and these would be density independent. Again, be able to look at this graph and be able to link these two together. All right, we moved on to community. Oops, nope, not community ecology yet. We've got the metapopulations. So metapopulation, we defined it, smaller subpopulations, and they can move. You can get a loss. So here, for example, we don't have a bat subpopulation here, but this whole entire region, maybe these are different woods, makes up a metapopulation. So we've got, these different subpopulations. And again, they can move from place to place. Over here, we looked at boom bust cycles. Honestly, this is not going to be on final. So you can look over this, remembering that the relationship we have sometimes we looked at the relationship between the snowshoe hare and the lynx. Metapopulation, you might want to know that. All right, then we moved on to community ecology, and we started off with looking at species interactions. So we had defense mechanisms, we had mechanical, quills, anything you've got, an armadillo and its plates, chemical defense, where we've got toxins, the dart frog, coloration, let's talk about that in a little bit more detail next, and camouflage. So those are all ways that species try to defend themselves. When we talk about coloration, we have mimicry. Oops, you know what? So the other thing we talked about was when we're talking about exploitation, we're talking about defense from exploitation. And we call exploitation a positive negative, where it's positive for one organism and negative for the other. So our examples were predation, something that's going to hunt and kill other organisms, and herbivory. Cows eat grass, we eat lettuce, and lettuce plants and organisms. So what's good for us isn't so good for the plants. All right, when it comes to camouflage or coloration, we have two types of mimicry. So these are mimicry. We have Batesian. So these guys are Batesian. These guys are Mullerian. Batesian, a harmless organism, looks like one that's dangerous. So the non-venomous king snake looks like the venomous coral snake. This is a moth that looks like a snake. So that's Batesian. Mullerian's when you get a similar pattern between species. So you'll see like on bees and yellow jackets and some wasps, they all have this yellow-black striping. Same. Now, people used to believe that the viceroy was not, they said this was Batesian. It's actually Mullerian, where the viceroy also has a very bad taste. Another one we talked about was behavioral. We looked at the mimic octopus, and it can make itself look like other organisms. So here it looks like a zebrafish. Here it looks like a snake. So mimicry can take a lot of different forms. We have symbiosis, where we talked about mutualism. Mutualism is a positive positive. Commensalism is a positive zero. And parasitism is a negative negative. They give you examples here. Another one we talked about were birds on the grazers on the African plain, where the grazers kick up bugs and the birds can eat them and the grazers really aren't harmed. Or commensalism. Up here, we talked about, of course, the clownfish and anemones. We talked about, oh gosh, what else did we talk about? We talked about lots of examples here. Of course, parasitism, ticks on cats or people, fleas, lots of examples of parasites. I think I'll make the stopping point in this video. We'll go into resource partitioning. So a niche is an area in an ecosystem that an organism lives or is found, and it is affected by competition. So competition is a negative. So a fundamental niche is a area where a species could occupy, and a realized niche is an area where species actually occupy. And they did an experiment where they have, I assume it's pronounced thalamus barnacles versus, what are these other guys called? Balanus barnacles. So let's see, who is the thalamus is pink. So the thalamus can live in this region, and the Balanus only can live here. So what happens is, because of competition and to avoid competition, the thalamus has a smaller realized niche than it does a fundamental niche. And we call this competitive exclusion. So we get competitive exclusion here. Where the thalamus are excluded from this part of their fundamental niche in order to avoid having to compete with the Balanus. And we could say it's an advantage between two species vying for the same resources. It will cause the advantage species to take over the niche. So you see that this barnacle takes over. They could both exist here, but it's taken over by the Balanus. We have resource partitioning. And this is where natural selection forces competitors into different niches. And we're looking at different types of, I forget if these are warblers or sparrows, but you can see this one eats here. This one has this part of the tree, this part of the tree, this part of the tree. So very, very specific areas of the tree where they'll go. Or we have water birds, and the shorter the legs, so we've got longer legs, and the shorter the legs, in this case, the duck can reach further. So they don't compete with each other. After a while, we can also have time, where we can have diurnal versus nocturnal. And the result is we get character displacement. So character displacement, where we get speciation, we get a new species that arises, and this is a result of that sympatric separation, and the traits diverge. So that's kind of the end game. Okay, that takes us into, we're getting into, I'm gonna jump around a little bit. I want to jump ahead, and I'll come back to this slide, these two slides later. I want to put diversity on this one. So diversity is your proportion of species, and we use what's called, so we have richness of species, and that's the number of species in a given area. And diversity is the proportion of species, one type. So up here, we're looking at mushrooms, or you could look at the tree diversity. And for diversity, we use the Shannon Diversity Index. No calculations on the final like we had on the test. But you should know the difference between richness and diversity. And then we also looked at roles in the ecosystem. So we had ecosystem engineer, the beaver builds dams, and that affects the whole habitat. We have foundation species. Oops. They make up the base of the food chain. We have invasive species, species that aren't supposed to be in the food chain. So they're showing, I don't know if that's supposed to be a zebrafish. I think it's supposed to be a zebrafish. We talked about several examples of invasive species and how they're so detrimental. And then keystone species, those are top-down control. So be familiar with those terms and an example or two of each. Okay, and then we'll make the last video for ecology. It'll be video number 6, energy. So we'll go back and we'll pick up trophic levels and food webs in that video. Okay, that'll be it for this one. See you in the next one. Maybe. Gee, can't get rid of my, there we go.